Alright, so in our previous lesson, we introduced vectors in space, and our main idea here was we wanted to see the similarities between what we were doing with vectors in 2 dimensions and what we're doing now with vectors in 3 dimensions. And like we said, there are a lot of similarities here. As you can see here, if we have vector addition, it's the same concept as vector addition in 2 dimensions, except now we have the third components that we're adding together. With scalar multiplication, we're adding a vector, or we're multiplying a vector by a constant. Again, you're just multiplying all 3 components by that constant. All right, so it's not anything super difficult, but it's just a matter of applying it to this third component. Likewise, the same principle we saw earlier about the fact that if you multiply a vector by a constant, it multiplies the magnitude by the constant. That still applies here even in 3 dimensions. Okay, so let's run through these real quickly. If I were doing u plus v, and u was 3, 8, negative 2, and v is negative 4, 6, 5, what would u plus v be?
Wait, wouldn't it be u?
Yeah, 3
plus
plus negative 4, so that's
Negative 1.
negative 1, okay.
Yeah, and that would be 8 plus 6.
8 plus 6 is
14.
14.
Then minus 2 plus 5, which is minus, 3.
Yeah, okay. So that's all there is to it. Let's take this 3u minus 2v for a second. What would 3u equal?
9, 24, negative 6.
Yeah. And then if I need to do a minus 2v, what's negative 2 times v?
So,
8, negative 12, and negative 10.
Yeah, okay. So now we add those together, and we get 9 plus 8 is 17. 24 minus 12 is 12. And negative 6 minus 10 is a negative 16. So there we have our resultant vector, the 3u minus 2v. Okay? All right, then how did we do magnitude of a vector? You guys remember?
Like the, distance. I don't know. I call it the distance. Like you did Pythagorean.
Yeah, it was the Pythagorean theorem, which is the distance formula is directly derived from. Okay, so before we were doing the square root of the horizontal component squared plus the vertical component squared, but now we have an x, we have a y, and we have a z. So we just throw that in as well, minus 2 squared. Okay, so we have now the square root of 9 plus 64 plus 4. 68, 77, square root of 77 would be the result. Okay? So then what would the magnitude of 5u equal?
3 times 5. 15 squared,
5.
right? Oh wait, actually no, is it
5
root 7?
What? Yeah, just do times 5. 5 times radical 77.
Yeah.
There you go. That's it. Okay? Now, the one nice thing about this, how this can be used. Okay, thanks. The nice thing about this is that you can also do things to make the calculations a little easier. Like, we could do 48 squared, negative 72 squared, and 24 squared. Okay? Or, notice w has a common factor here, doesn't it? All 3 of those components are multiples of what?
8, right?
8. even more than that, though. There's even bigger number. Huh? Even more than 12.
I have no idea what.
Huh?
14.
4, not 14. 24.
24.
Actually, I could rewrite W as 24 times the vector 2, -3, 1. So, if I wanted to do the magnitude of vector W, I don't have to square 48 or 72. I could just do 24 times the square root of 2 squared plus a -3 squared plus 1 squared. So 4 plus 9 plus 1 is 14. That's 24 root 14. Okay? So that's one way you can use the property here with the magnitude to make your life a little bit easier. Keep the numbers nice and small. Okay? Alright, so one of the things that we will do here a little bit is doing some algebra with vectors. And really the only difference between doing algebra with vectors and doing algebra with just variables is the fact that we don't technically have division. All we have is multiplying by the reciprocal of a constant, which is what that's the definition of division anyways. Okay? So, for example, I could, in this first case, subtract 3u from both sides, and I'll have 2v equals w minus 3u. Okay? And then what I would do is I would multiply both sides by a half. Alright, so I got to distribute it to both parts on the right. So vector v would simply be 1/2 vector w minus 3/2 vector u. Okay? So that's not too bad. Same thing here with number 5, or with the 5 times u minus v equals w. If I want to solve that for v, I can multiply by a 1/5 times 1/5. So then I have u minus v equals 1/5 w. And then I'll add v and subtract 1/5 w, and I'll get vector v equal to u minus 1/5 vector w. Okay? Now this is helpful when we're trying to find, say, a vector that needs to be implemented into a situation when we know what the result is. We want a particular result. We've got to figure out we've got to figure out what vectors need to be put in there. And we might know one of the vectors, but okay, what's the other vector we need to implement here to get the result we want? And that's kind of the idea that we're using here. Okay? This is just a quick review of a principle that we looked at earlier. When we looked at the magnitudes, we saw that we could make a unit vector by multiplying a vector by 1 over its magnitude. That's what this first one is. If we want to then change that magnitude to be something else, we can multiply by that value, in this case k. K over the magnitude of v will change the magnitude to whatever you want it to be. Okay? So, for example, if I want a unit vector parallel to this vector 12, 10, 6, the first thing that I need to do is what? Multiply by 1 over what?
The magnitude.
The magnitude of this, okay? So I need to figure out what that magnitude is, right? So, I know what I need to do. Okay?
The square root of those.
So yeah, go ahead and take a minute and find that. Alright, so if you do this, the magnitude here is going to be the square root of 144 plus 100 plus 36, square root of 280. Now, whether you choose to do decimals or fractions, I mean, fractions are nice because they, in simplest radical form, because they keep your answers exact. All right, so like 280, the square root of 280, there's a 4 in there, so that's 2 root 70. And then 70 is 2 times 35, so that doesn't simplify any further. So we can multiply by a 2 root 70 here, or 1 over 2 root 70. And then our vector would simply be, if I reduce it by the 2, 6 over root 70, 5 over root 70, and 3 over root 70. Okay, notice the 2's canceling out here. Alright, and then if we do simplest radical form with that, it would be 60 root 70 over 70, 5 root 70 over 70, and 3 root 70 over 70. And some of those, well, the first one would reduce. 6 over 70 would be 3 over 35. So we could make that a 3 over 35. And then that would be the unit vector in the same direction or parallel to 12, 10, 6. So one thing that can be a bit of a challenge here in our unit on vectors is our notation. Okay? And so as we see here, we have vector AB and we have vector BC. We want to get vector AC. Okay? Now, it's not too hard as long as you think. The times when students mess this up are times when they just add stuff and don't really think about what exactly they're doing. It's not a difficult thing, but it's just a thing that you have to pay attention to. Okay? So here, if I want to go from A to C, I need to make sure that the vectors that I add start with point A and end up at point C. Alright? So for example, in this case it's kind of set up nicely for us. We have vector AB plus vector BC. So we're going from A to wherever B is to wherever C is. And the end result is I'm going from A to C. If you think about it and visualize it, it's a pretty simple concept. All right. So now, as I'm doing this addition, personally, I would rewrite these in a form that's a little bit more user friendly. 1, negative 1, 1. Remember the IJK notation is just another type of writing these vectors with the coefficients. Negative 2, 1, negative 3. Okay? So now if I'm doing that vector addition, I have 1, negative 1, 1, plus, plus negative 2, 1, negative 3. So the end result is a negative 1, 0, negative 2. Okay? So that is my end result for vector AC. Okay? There will be times where you may have to rewrite one of these. Okay? For example, let's say I was given vector AB, but then I was given vector AD. Okay? if vector AD was, say, the vector 3, 5, negative 2, let's say I wanted to find vector DB. Okay? Vector DB. First of all, I'd have to start with a vector that started with D, and I would need to end up with a vector that ended with B. Okay, and add those together.
Started with D and ended?
Yeah, so we don't have any that start with D, but what could we do? The only one that has a D in it is AD. What could we do with that?
Multiplied by -1.
Yes. Yes, okay. If I want DA, that's just the opposite of AD, okay? So DA would equal a -3, -5, and a +2. Okay? Well, now I have DA, and then if I need to get to B, that means I'm at A, so I'm going to go from A to B, and I have that vector. So now it's just a matter of -3, -5, 2, plus 1, -1, 1, and I get my result, -2, -6, 3. Okay? So that's not terrible. It's again very similar to stuff we were doing in 2 dimensions, but the key here is to keep going and just to find how do I get, if I want DB, how do I get from point D to point B? Okay? It may be helpful to draw them, even though in 3D you don't need to draw them super accurately, okay? All we care about is that we have 4 points. All right, so if I threw in another point over here, point D, okay? There's the vector I gave you. Wait, sorry. I gave you vector AD. Yeah, I gave you that one. If I want to go from D to B, then that means I've got to go from D to A and then from A to B. See how that works? And when you draw it out like this, oh, I've got to go D to A, that's just the opposite of AD. That kind of helps you visualize the process a little bit. Okay?